Okay, in this lecture we calculate the capacitance for specific types of plate geometries. There are three specific plate geometries that we have to be familiar with when calculating capacitance. The easiest of the three, and the first that we'll begin with, is the parallel plate capacitor. Now when calculating capacitance, we're working with the following expression. Charge equals capacitance multiplied by voltage. So basically what we have to do are voltage calculations. Once we do voltage calculations, we then divide it out to the left-hand side in the denominator of the expression, and this then gives us the capacitance C. As we'll see, capacitance is basically dependent upon two things. It's dependent upon the area of the plates themselves and how far apart they are from each other. In other words, it's essentially dependent upon the geometry of the situation. Okay, so let's begin with the parallel plate capacitor. That's the first of these three problems. Go ahead and copy it down into your notes. So a parallel plate capacitor consists of two oppositely charged plates, each with an area charge density sigma, plate area A, and separation D. Ignoring edge effects, find the capacitance. Okay, so here is that parallel plate capacitor like so. Let's say that, for example, this right here is the negatively charged plate. Here's the positively charged plate like so. So then therefore the electric field looks like this. Okay, recall that the electric field has a magnitude of sigma over epsilon naught. This was a calculation back in Gauss's law in chapter 22. And we already know what the potential difference is if the plate separation here is D. The area of the plate, however, is A. Recall that the potential difference from a calculation that we did back in chapter 23 for electric potential is the student's name. V equals ed. Like so. So because we already know that calculation from a previous problem, let's go ahead and plug it here into this side of the expression. So Q equals C times V, which is E times D. And then the Q, how do we deal with the charge? Well, this is where the charge density comes into play. So charge is equal to charge per area multiplied by area. So that then goes over here into the left-hand side of the expression. Like so. And now we'll just divide out by E times D, where E, the electric field, is sigma over epsilon naught. So the capacitance then is sigma A divided by E times D, sigma over epsilon naught times the plate separation D. The sigma cancels out, like so. Last step is to move the constant epsilon naught up to the numerator of the expression. So as I described in my opening lecture on capacitance, basically capacitance depends upon two things. It depends upon the area of the plates and how far apart they are from each other. In order to make the capacitance as large as possible, to store as much energy as possible, you want to make the plates themselves with a really large area, and you want to have the two plates as close to each other as you can possibly obtain. Okay, so that's the first of three calculations, and as you can see, this calculation here is pretty easy. What you have to do pretty much, however, is commit this expression here to memory or know how to quickly derive it as I did here. Okay, let's move on to the next example. I need to move my file to do so. This is for the spherical capacitor. All right, so let me move my file. Okay, let me erase. Okay, now the spherical capacitor is as follows. Find the capacitance of a spherical capacitor. The spherical capacitor consists of two thin, concentric conducting shells with opposite but equal charges Q and radii A and B. So right here is our spherical capacitor, like so. Okay, each of these spheres that I'm drawing here are very thin, spherically conducting shells. So this is really thin, this is really thin. This is empty space, this is empty space, this is empty space. Okay, and then we have radii here, A, B, like so. Let's make the inner plate the positively charged value. Let's make the outer plate the negatively charged value. It actually really doesn't matter which one is which, but let's go ahead and set up the calculation in this manner. Okay, now capacitance is equal to charge divided by voltage. So basically what we have to do here is just a voltage calculation between points A and B on the diagram. Once we have done that, then we basically just plug it into the denominator of the expression. All right, now the electric field here in this case from Gauss's law is as follows. Okay, the electric field inside this cavity here is equal to 0 because there's no charge enclosed. And then in between A and B, you have a point charge electric field that looks like this. Like so. So if we used Gauss's law here between points A and B on the diagram with a spherical Gaussian surface, we would find, of course, that the electric field is equal to the Q enclosed, which in this case is the positive value, divided by 4 pi epsilon naught, and then multiplied by r squared. So that's, of course, just our Gauss's law calculation as we've seen multiple times already. Incidentally, outside of the capacitor, the electric field is equal to 0 because there's no Q enclosed. The total amount of Q that's enclosed is equal to 0. Okay, now that we have our electric field, let's then calculate the potential difference as we go from here to here on the diagram. We'll consider this to be point A on the diagram with radius A, and this right here to be point B on the diagram with radius B. So in order to do so, we'll do VB minus VA equals negative integral A to B, B dot DL. Okay, so this right here is going to be the potential difference from here to here. We're just going to refer to that as V, as we do when talking about circuits, for example. So this right here is just V. And then on the right-hand side of the expression, we have our integral. So we're integrating from A to B of the electric field. There we go. Like so, in the radial direction. So integral of negative 1 over r squared is positive 1 over r. Like so. And then we evaluate this from A to B. So then therefore, the potential difference is equal to the following. Like so, 1 over B minus 1 over A here in parentheses. Okay, now is this a negative number or is it a positive number? Well, B on the diagram above is a number that is greater than A, so then therefore this is overall a negative number. But negative sign, however, doesn't matter because we're just interested in the potential difference itself. So then therefore we could write it as we did here as 1 over B minus 1 over A, and we would just take the absolute value of it. Or if you wish, you could actually just take the two terms and reverse them. That's fine. So it's important to just do the potential calculation itself, the potential difference calculation, but then we just want the positive value of it. So then therefore, if necessary, you can take the two terms here and switch them. So I'm going to go ahead and write it like this. Like so, just to make it a positive value. Okay, then therefore this expression here for the potential difference between the two plates, that then is what goes up into the denominator of the blue expression on the top board to now do the last step to calculate the capacitance. So the capacitance is Q over V, so Q over this quantity. Like so, the Q's cancel out, like so, and then we just take the 4 pi epsilon naught and move it up into the numerator of the expression. So, okay, now just to kind of check ourselves here, let's compare this capacitance that we just calculated for the spherical capacitor to what we did a little while ago for the parallel plate capacitor. Take a look at the expressions. They have the same mathematical form. Basically, epsilon naught multiplied by area divided by distance, which would be like meters squared divided by meters. It's like epsilon naught multiplied by a length in terms of meters. We get the same thing here. We get epsilon naught and some constants, but we get epsilon naught and then divided by 1 over meters, if you will. So then therefore it's epsilon naught times meters. You'll always end up with the same sorts of expressions when calculating capacitance. Once again, basically what we're calculating here is based upon geometry. Okay, and then there's one more example for us to look at, and that's the cylindrical capacitor. Let me go ahead and do some erasing here, however, first. Like so. Okay, let me move my file. Okay, now for the cylindrical capacitor is infinitely long. So then therefore, for that reason, we're going to calculate what is referred to as the capacitance per unit length. So we're going to do our calculation much like I just did for the spherical capacitor, but then in the last step, what we do is we just divide out by the length. This then gives us capacitance per length. Okay, so find the capacitance per unit length of the cylindrical capacitor. The cylindrical capacitor consists of infinitely long conducting concentric cylindrical shells with opposite but equal charge Q and radii A and B. So let's draw it like this. I'll use my blue marker to do so again. Like so. Like so. And then for this cylindrical capacitor, this right here is a very thin conducting shell. This is empty space. This right here is empty space, and this right here is a very thin conducting shell. Okay, this right here is inner radius A. This right here is outer radius B. Okay, once again, let's place the positive charge on the inner plate, if you will. It doesn't really matter which one is which. Here's the negative, like so. And then from Gauss's law, the electric field is equal to 0 in here. And then in the in-between region, it's radially outwards from the inner plate, like so. And then the electric field is equal to 0 outside because the Q enclosed is equal to 0. Okay, let's actually go ahead and do the Gauss's law calculation here that is necessary to find the electric field that is here in between points A and B on the diagram. So let's go ahead and use Gauss's law to do so. Like this. Okay, and now we're going to set up right here. I'm going to go ahead and draw it. Right here is going to be a cylindrical Gaussian surface, like so, with a radius small r. And then therefore on the left-hand side of the expression from Gauss's law, we'll have E multiplied by the surface area of that Gaussian cylinder, 2 pi r times the length L. This is where the length L comes into play. And then on the right-hand side, I'm going to just go ahead and write the Q enclosed here as the capital Q associated right here with the inner plate. So the electric field then, its magnitude is equal to this quantity here. Like so. And then it's this electric field that we then have to integrate as we go from, say, point A to point B on the diagram. Okay, so let's find the potential difference between the two by setting up our expression like so. Okay, once again, we'll just write the potential difference here as V. And then we have the following. We integrate from A to B on the diagram of electric field. So Q over 2 pi epsilon naught L R. And we integrate, of course, in the radial direction. Okay, notice that we're going to get a natural log here for our calculation. So then therefore I get negative Q over 2 pi epsilon naught L, and then multiply by natural log of B over A. Like so, okay? All right, so I end up with that expression there as my potential difference between points A and B on the diagram. Okay, B is a bigger value than A is, so here in parentheses is a number that is greater than 1, therefore you end up with right here a positive number. However, this negative sign here, once again, really doesn't mean anything when we're just talking about the potential difference itself. So let's just go ahead and take the absolute value prior to plugging this expression into the denominator of the expression for capacitance. So we'll just take the absolute value, and now the capacitance is Q over V, so Q divided by Q over 2 pi epsilon naught L, natural log of B over A. So the Q's cancel out, like so. And then we'll move all of this stuff here up to the numerator. And that then gives us the following expression, like so. Notice that the units here are epsilon naught times the distance. It's epsilon naught times meters. There are no units associated with the natural logarithm. The capacitance, technically speaking, however, is infinitely large because after all, we're talking about infinitely long cylindrical shells. So then therefore, this is why we do the last step in the problem, which is to calculate the capacitance per unit length. The capacitance per unit length is then therefore equal to the following. 2 pi epsilon naught divided by natural log of B over A. So these are the three plate geometries that all introductory students have to be familiar with. First of all, the parallel plate capacitor, which is the easiest one to evaluate, and it's the most common one that appears in various exams and so on and so forth. But you also have to be familiar with the spherical and the cylindrical capacitors as well.